Hi, my name is Tanner. I'm a Master's of Geology student at Bowling Green State University, and today I'm going to be watching Have We Really Found Life on Mars by Astro. So this seems pretty interesting. I think Mars's geology is going to be really interesting, and I'm sure that's a huge part of what this covers.
You've likely all seen the news by now. NASA found a possible sign of life on Mars. These tiny spots, barely visible to the naked eye.
Yeah, I think they were calling these like leopard spots. And at least if I remember correctly, the thought is that these spots show like a geochemical composition that could be associated with life interacting with the atmosphere would leave behind. There are like certain minerals that are there that would typically only show up with living things is kind of my impression, but I don't know too much about this. I'm not like a planetary geologist, so I'm really curious to see exactly like how likely it is that life does, or at least once existed on Mars.
Are the biggest space news in over 50 years. If this really is a sign of life, it would be the most meaningful discovery in the history of humanity. But we've been burned by false alarms before, so have we really done it this time? I'm Alex McColgan and you're watching Astrum. Join me today as we dig into the details of what Perseverance found, why scientists are excited, and what it will take to prove we're not alone in the universe.
Very grand, dramatic, thematic
In
intro.
2021, NASA's Perseverance rover, or Percy to his friends, touched down on an ancient Martian lake bed. The Jezero crater was once home to a large body of water, with rivers flowing in and out, carving
Just like a
deltas
huge crater.
and carrying sediment.
Yeah.
The soil is rich in clay minerals that can only form in the presence of
Water.
Percy has been sent to hunt for ancient microbial life. If it's going to find them anywhere, the Jezero crater seems like a good bet. You see, ancient lakes often contain perchlorate, which can be metabolized by microbes. Astrobiologists on Earth study microbes like this in extreme environments to understand if life could survive.
Looks like a
in
black
similar
smoker.
conditions
Yeah.
on other planets. The rover's job is to look for these possible signs of life, identify and store the most interesting samples of Martian rock, and prepare them to be collected by another space mission for an eventual return to Earth. One day, in July 2024, while exploring the edges of the ancient Neretva Vallis River channel, Percy's cameras spotted something unusual. A rock from the Bright Angel Formation. Two of the rover's instruments, the Planetary Instrument for X-ray Lithochemistry, or PIXL.
Yeah, so so the Bright Angel Formation, I guess, is like relatively renowned for its because it's a Martian like sedimentary rock layer. I don't know too much about it, but I have talked with my advisor about it, and apparently it's really like really crazy and like really something. This is like a geochemical like scanning equipment, which I believe is like one way that geologists like understand the geochemical composition of rocks. Same way like some physicists do when they're doing like material scientists, which are some geologists are material scientists. They're just like a specialized type. So basically what they do is they get an X-ray gun, they shoot those X-rays at a specific rock type, and depending on the angle at which it bounces off that sample, you can tell like specifically what kind of compounds are there or what types of elements are like tend to be common there. And sometimes you can even see like the specific crystallizations of certain types of compounds. So it's very, very useful for figuring out like, oh, this is like a chunk of an igneous rock that's in here, or oh, this is like a very specific type of like chlorite-rich mudstone, or maybe this is just clay-rich like sandstone. Very cool.
Scanning habitable environments with Raman and luminescence for organics and chemicals, or Sherlock for short, detected sedimentary rocks made of clay and silt. On Earth, these materials are excellent preservers of microbial life, so Percy took a closer look.
Yeah, you want to target those good sedimentary rocks.
Amazing. The rock, also known as Chayava Falls, was rich in organic compounds like carbon, phosphorus, and iron, arranged into rings.
Yeah, that is like one of the things you have to think about, like whenever you're looking at like for chances of life, is kind of like what if you expect life not to be there, you have to have like kind of like this baseline expectation of like, oh, if life isn't here, this is what it would look like, and if life was maybe here, this is what it would look like, and you have to compare those and be like, does this look, and try to think of it from like, what is the most reasonable explanation? Is the viewpoint that aligns the most evidence that we are seeing, or the strongest evidence that we are seeing, is the easiest thing to believe? Is that there is life, or is that there is not life? So you have to have a really high barrier, like life from other planets, because we just really haven't seen like any other evidence of it. If this really is something, you just have to find like a ridiculously high, like credible amount of evidence. And this could be it. So it's really spectacular.
Affectionately named leopard spots and poppy seeds,
Leopard
the
spots
tiny
and poppy
spots
seeds.
span 200 micrometers to 1 millimeter in diameter. But it was enough to raise the blood pressure of astrobiologists everywhere. The light inner part of the leopard spot is chemically similar to the surrounding rock, but the dark outer rim is enriched with iron and phosphorus. It seems to be evidence of localized iron reduction. Percy also
Interesting.
detected organic carbon-based compounds in the rock, and based on its texture and geochemical composition, we strongly suspect this rock was once in contact with water. Usually, when we see such a combination of organics, water, and iron reduction on Earth, it's interpreted as a sign of microbial life. Suddenly, NASA had something very unique on its hands. Could this mudstone rock hold the first alien biosignature ever found? At the center of this story are two very special minerals, vivianite and greigite.
Yeah, so Vivianite
is an iron phosphate.
Okay, yeah, Vivianite. What's crazy about this stuff is actually sometimes when you have people who have died and their body is like kind of in the process of breaking down, Vivianite sometimes like precipitates on them because iron from their blood mixes with like the phosphate from other parts of your body that are breaking down, and you just see like a huge crystal like start growing. So that's just like a fun fact.
On Earth, it forms near metal ores and river sediments, where microbes like Geobacter metabolize iron instead of oxygen. They take in iron 3 oxide and release iron 2 as a waste product. The energy given off by this reaction then powers their metabolism, a process known as chemosynthesis. When the expelled iron 2 reacts with the phosphate and the water in the environment, it forms vivianite. Greigite follows a similar story. Sulfate-producing microorganisms on Earth break down sulfate into sulfide, which reacts with iron to make greigite. But let's be skeptics for a moment and rule out microbes for now. What else could have caused these reduction
Yeah, that's the big
reactions?
question.
Well, one explanation could be very high temperatures. The sulfide needed to produce greigite could have come from volcanic gases leaking into groundwater. But that means the sulfide would have had to migrate from a hot volcanic system into a much cooler environment, and there's been no evidence for such volcanic or hydrothermal sources nearby. Another possibility is that sulfate in the rocks was reduced to sulfide through reactions with organic matter. But unless temperatures exceed 150 to 200 degrees Celsius, these reactions would be very slow and require a huge amount of energy, making them unlikely. And studies of the rocks around this area have shown no evidence of high temperatures. So there's no way the surrounding environment could have got hot enough to reduce sulfate and form greigite. Another possible explanation is acidity. Both iron 3 ions and sulfate ions dissolve much more readily in water under acidic conditions than they do under neutral conditions, making them much more prone to reduction through purely chemical reactions. If the water on Mars was more acidic than we anticipated, that could have caused the spots Percy saw.
Okay, so that
Perhaps these
seems like a
spots
real
were just the
possibility
result
then.
of chemical processes on an alien planet, nothing more. But then Percy spotted this little green mineral. nestled near the sample site,
Is
a
that
small
olivine?
rock of olivine
Okay.
knocked the acidic water hypothesis on its head.
Oh yeah,
Olivine-
because one thing that's fun about olivine, it tends to form in places that have very strong like mafic compositions. So this is like very iron rich. Think of like a very iron rich magma. Olivine is, I believe, it's made of forsterite and for phaolite, it's Fe2SiO4, I believe, and then for forsterite, it's Mg2SiO4. And that tends to be like the grayer version, if I remember correctly. Yeah, it tends to interact very strongly with like the atmosphere, so which is kind of like doesn't last very long, at least on Earth's surface. Breaks down very rapidly. So when you find it, it's like, oh wow, there's volcanic activity likely like very close to here.
is the fastest weathering silicate mineral. Unlike
Yeah,
other
that's what he's
silicon
saying.
structures like silicon dioxide, for example, olivine doesn't have strong silicon-oxygen silicate.
Okay, yeah. So one thing that's also fun is the rocks he's looking at right here. These are, I believe these are called xenoliths. So imagine the Earth has four main layers. The one that we live on is the crust. Below that is the mantle. Below that is the inner core, and below that is the outer core. So sometimes you have things like chunks of the mantle that get shot up to Earth's surface, and we call these xenoliths, and they tend to be very rich in olivine. So imagine like the mantle, if it was cool enough that it wouldn't be like red hot, it would look greenish, which is always really fun to picture. But if you take a look at like these chunks right here, since they're right next to like a black like basalt, I imagine magma came up and it ripped out like huge chunks of the mantle, and you can see like these huge chunks as like these like greenish spots on this rock. Very
bonds.
cool.
Instead, it's made up of negatively charged silicate ions held together by the electrostatic attraction with positively charged magnesium and iron ions. In acidic conditions, these are displaced by hydrogen ions, breaking olivine down into orthosilicic acid and magnesium ions in solution. The more acidic the environment, the more hydrogen ions there are, and the more aggressive the dissolution of olivine would be. So the very fact that it exists rules out the possibility of acidic conditions causing the strange spots. When studying signs of possible extraterrestrial life, Perseverance needed the best camera it could carry. Mission constraints make heavy, bulky gear impractical. And when I'm shooting space, I don't want anything too big or heavy either. I recently tried the Dwarf 3 Smart Telescope from Dwarf
Okay,
Lab,
this is
today's
like
sponsor,
an ad.
and this compact
I'm gonna
device
skip past
really
that
impressed
then.
me. Whether you're a big Astrum 5
Okay.
at checkout, it is ultimately about falsification. It's not about proving a hypothesis true. Much more often, it's about proving a hypothesis false.
Yeah.
Over time and through a
Big part of
process of
science.
elimination, all roads seem to point to the same explanation. And if that explanation holds up against enough skepticism for long enough, it eventually becomes an accepted theory, testable, reliable, and widely accepted by the scientific community. In this paper, the Mars research team tried to prove that these minerals were not left behind by ancient alien life. They started with a null hypothesis and systematically investigated all the non-living explanations for what they found.
Yep, that's like the right way to do science. You want to, find the easiest way to explain something, because the easiest way is almost always like generally what happened, because it's generally just like the most likely.
But after months of study,
If you try to explain it very hard with a lot of these things that seem like very easy, sometimes you can end up in a place where it's like, oh, the easiest explanation is just that this is alien life, which is really crazy, but that could be true with these certain deposits, because they were talking about it being like specifically associated with reducing conditions, which makes sense with like certain types of like chemosynthetic bacteria. Maybe those in some capacity like existed on Mars.
they concluded they just couldn't do it. Now, saying we can't explain how this was done by something non-living is very different from saying this is a definitive sign of life. For one thing, all our speculation and contained excitement is based on what we know about biochemistry on Earth. And no matter how tempting it may be, We cannot allow ourselves to assume that just because something happens one way on Earth, it would happen the same way on Mars. Maybe it has a totally different biochemistry we know nothing about. NASA's being extra careful not to say too much too soon. After all, we've been wrong about potential biosignatures on Mars before. Back in 1976, the Viking lander tested Martian soil for life by squirting it with nutrients labeled with radioactive carbon-14. If microbes were present, they'd metabolize the nutrients into radioactive carbon dioxide we could detect. And to everyone's shock, that's exactly what happened. Excited scientists thought they had proof of alien life. But in 2008, NASA's Phoenix lander found Martian soil to be rich in perchlorate, a powerful oxidant that destroys organics and releases gas when heated. What looked like a biological reason was really just chemistry, a false positive. Still, Mars kept dangling hope. In 1996, a photo of meteorite ALH 84001 made headlines. The rock itself was over 4 billion years old, from a time when Mars had
Oh, that's
liquid water
crazy.
on its surface. Under the electron microscope,
I remember that one.
resembling bacterial colonies. The world stood still. Researchers thought they were onto something big, so big that President Bill Clinton gave a formal announcement about the discovery. Sounds a lot like NASA's recent statement of Perseus discovery, doesn't it? But in 2022, those squiggles were ruled non-biological, explained instead by a water-rock reaction called serpentinization, another false alarm. So, is our recent finding in the Jezero crater another close call? Or is it proof that the third time really is the charm? There's only one way to find out. We have to bring the sample home for further testing. That's where the Mars Sample Return mission comes in. It's a complex mission, which requires sending 3 separate spacecraft to Mars. Percy has already completed Phase 1. It's drilled into Chayava Falls and tucked away a precious core sample of the mudstone rock mission scientists named Sapphire Canyon. Phase 2 would be to send another spacecraft to land near Perseverance, collect those tubes, and launch them into orbit around Mars. The third and final craft would collect the samples from the orbiter and ferry them all the way back to Earth. It's a huge task, with an estimated price tag of $11 billion. The Mars Sample Return mission was first announced in 2022 as a joint collaboration between NASA and ESA. Since then, it has been fraught with financial struggles and uncertainties, delaying the project from 2033 to 2040, before ultimately being suspended indefinitely. This is despite the National Academy of Sciences Decadal Survey, a meeting of leading scientists who get together every 10 years to decide the future priorities for progress in STEM, naming the Mars Sample Return as the highest priority for NASA 2 decades in a row. And that was before we discovered this potential biosignature on our neighboring planet. All we can do is hope this puts political pressure on leaders to mobilize the necessary resources to pull it off. So, if we ever do get the Sapphire Canyon sample back home, what kind of experiments might scientists run? There's a good chance that, among other things, they'll be looking for 2 key fingerprints of life. The first is chirality. Amino acids come in 2 mirror image versions, right-handed and left-handed, also known as D and L amino acids. On Earth, life overwhelmingly prefers the L version of things, while non-living materials show more of a 50-50 split. If the Martian sample shows a significant chiral preference, either right or left-handed, that could be a smoking gun. The second fingerprint is carbon isotopes. Carbon comes in a few different flavors, most common.
Okay, yeah. So I think here what they're going to talk about is they're talking about different isotopes of carbon. So they're going to talk about, I believe, like life has a preference for carbon 12 versus carbon 13. So whenever you like investigate some of this stuff, you should see if it was likely at least had life in it for a little bit. You should see a preference for carbon 12 as opposed to 13.
Commonly carbon 12 and carbon 13. Again, life prefers one over the other. The ratio of carbon 12 to carbon 13 in living things is much higher than in non-living things. If we see a similar pattern in the Sapphire Canyon sample, that could be another clue that its origin is biological. You see, you and I may often think of discoveries like these in quite a binary way. Either they're a sign of life or they're not. But NASA has a much more nuanced take. They recently proposed the Confidence of Life Detection Scale, a framework for ordering how likely discoveries actually are to be signs of life based on a set of criteria. It has 7 levels, ranging from we found something that could be caused by life, all the way to multiple teams have independently confirmed life more than once. NASA hasn't stated where the discovery in the Jezero crater falls, but I'd guess probably somewhere between levels 3 and 4. If the samples come back and independent labs around the world all confirm that what we are seeing really did come from a biological origin, that would push us up to a level 6. Level 7 might even require going back to Mars and finding the same evidence in a completely different location. So, when NASA says this discovery could be the clearest sign of life we've ever found on Mars, they don't mean to say it is clearly life. But the Mars sample return mission
It does
could
mean
finally reveal
something to be
always been
investigated
alone in the
further,
universe, or
although it's not
did we
100%
once
sure.
have a cosmic neighbor. Even if our sample turns out to not be life, it's still an extraordinary discovery that will help us understand our own origins even better. See, we think Mars is like a time capsule of an early Earth. Unlike Earth, Mars doesn't have any continental drift or an active plate tectonic system.
It used to have at least some things that we think were tectonically active. Like there was a huge rift, I believe, in like the midsection of Mars, where we believe that it's like, oh, you know, there was probably some tectonic action there, some like shearing, some splitting, some stuff going
Its crust
on.
has been frozen in place for billions of years, preserved in a way Earth's crust could never be. The ancient landscapes on our planet have been erased through tectonics, erosion, oceans, and volcanism. So when we study Mars, we're not just asking whether it once carried life, we're also peering into a record of planetary conditions that resemble Earth at the dawn of biology. In that sense, Mars is a window into our own origins, offering clues to what Earth might have looked and felt like before life left its mark. But let's dream for a moment, shall we? What if the sample does turn out to be life? Well, most immediately, it would indicate that Mars was habitable far longer than we imagined, since the sample comes from relatively young sediment. But more importantly, we'd finally answer the question, can life exist on other planets? And in the same breath, open a Pandora's box of follow-ups. Did life on Earth start on Mars, or the other way round? Did a meteor from interstellar space seed life on both our planets? Or did it arise spontaneously twice? Where else could life exist in the universe? How common is it really? It would also have implications on the Drake equation, a probabilistic formula used to estimate the number of alien civilizations in our galaxy. The FL value here, which stands for the fraction of potentially habitable planets that go on to develop life, would jump from vanishingly small to closer to 1, since 2 out of 2 neighboring planets would then have or have had life at some point. An increase in this value causes the number of civilizations in the universe to shoot up. But crucially, this coefficient only changes if life on Earth and Mars rose independently. If we're related, the products of panspermia, that still represents just one biogenesis event, and the outcome of the equation remains unchanged. There's a concept known as the 0-1 infinity rule. In astrobiology, it represents the idea that life can only exist in 0, 1, or infinite places. We already know it's not 0. If it's just 1, then we're alone, a single spark in the dark. But if it's 2, Earth and Mars, then why not 5, 5,000, 5 million, or even infinite places in the universe? Suddenly, life isn't rare. We're not special anymore. And personally, I hope that if we ever discover life out there, it brings us closer together down here. Thanks for watching.
Okay, well, that was pretty good. Didn't go as into the geology as I hoped it would.